everyone, welcome to another interesting lecture on control systems. In today's class, we are going to be discussing about your steady state error in a first order or a second order system. So when I talk about steady state error, what it implies is, it implies the error that is taken after you subtract your feedback response from your input signal. So which means mostly your input signal is going to be R of S and your E of S is going to be something as R of S minus your G of S into H of S. So let us see how it looks in our feedback system. So this is my feedback system. So I have my system function, I have my input, then I have my negative feedback coming back to this system. And now if I have to label this is my G of S, this is my H of S, and my output is C of S, and my input is R of S. And the steady state error, the term that is important for my steady state error is my E of S. So as you can see here, the E of S is going to be the difference between R of S and the feedback loop that is coming back, and feedback loop which is sent back from the output, and that is going to be equal to C of S into H of S. And now I can write my C of S. So what is my C of S? My C of S is going to be E of S into G of S, right? So I am going to substitute C of S as E of S into G of S, because if you look at the system level diagram, I can easily write this formula where my C of S is E of S into G of S. Substituting this C of S back into my first equation, I'm going to get my E of S is equal to R of S minus E of S into G of S into H of S. Okay. Now that simplifies to E of S to one side, and then I get my R of S to one side, and that is further simplified to give my E of S to be R of S divided by 1 plus G of S into H of S. Done. So this is your E of S. So, and now the steady state error E of T is obtained by applying the inverse Laplace to this E of S. So the inverse Laplace of E of S is going to give you your ET. That is the error E of T. And now what if this, in order to make this error, or in order for this error to be a steady state error, your T must approach infinity. So then I have to apply my limits. T tends to infinity, E of T. Right, so that is your steady state error definition and also the mathematical representation. Now we'll be going on to see how to compute the steady state errors in first order systems and second order system, because if G of S is K by S, then that is your first order system. If G of S is K by S square, then you have a second order system, which means my steady state error is applicable to both my first order system and my second order system. And basically what do they represent? The steady state error just gives a tolerance, right? So it just tells what is the output and how much it is deviant from your input. So that any error function measures the variance, how it is, how much it is deviant from the desired value. So in this case also it is a steady state error, which means our steady state value is 1, and then how much it is deviant from that steady state value, and that is your steady state error. Alright, so now before we get into solving problems on steady state error, there are a few things we want to discuss. The first one of which is the final value theorem. The final value theorem states that the T tends to infinity on the time axis is equivalent to S tends to 0 on your Laplace transform or the S plane. So that is the transformation that final value theorem implies, and we can use that. So instead of doing T tends to infinity on E of T, because working with infinity is always inconvenient, whether you are a mathematician or you are a control engineer or you are just a science guy. So we all know that infinity is something that can't be quantified, and we don't want anything to do with it, right? At least, if we have a chance to avoid infinity, we always do. So in that way we can avoid infinity, and we can just take the limit s tends to 0 instead of that, and then my final value theorem states that that's going to be equal to s into e of s, and I already know what is my e of s, that is r of s upon 1 plus g of s into h of s. Good. So final value theorem lets me compute the steady state in a more quantified manner by keeping the limits in 0 and then solving for your steady state error. Next is the static error constant. So when I am talking about there are two, static, immediately it will come to your mind that what we also have dynamic error constants. Yes. So static error constant is something which works with only the terms in the denominator, right? So without the r of s. So if you see, the positional error constant is given by limit s tends to 0 g of s into h of s. Then your velocity error constant is given by this formula s into, and my acceleration error constant. So there are three static constants that we should be aware of, and these are the formulas, and it's very easy to derive these formulas, but for some reason I feel like I don't want to do it because it's not in your syllabus and it is not needed for you to know the derivation. But knowing these formulas is very important, and you may have to memorize these formulas because in your exams the question always comes: find the static error constants and find the steady state error. So the steady state error is more on the dynamic error constant, and your static error constant, meaning you have to find your Kp, Ka and Kv. Good. So that is for this slide. So now what all we have seen? We have seen the E of S formula, we have seen the final value theorem, then we have seen your static error constant. So now maybe we can see the steady state error for a step signal. So let us quickly do the step response. So whenever your input signal is a step, that is your step response, which means your R of S is equal to 1 upon S. Now, your steady state error is given by this formula ESS, which is equal to limit S tend to 0 S into R of S upon 1 plus G of S into H of S. Substituting R of S is equal to 1 by S, then what do I get? I get my limit S tends to 0, 1 divided by 1 plus G of S and H of S, and that is going to be 1 divided by 1 plus Kp. So I think this can be written as ESS is equal to 1 upon, so I can apply the limit only to the S term, right? So it will not be applied to the other terms. So I can just write this as 1 plus limit S tends to 0 G of S into H of S, and that is equal to 1 upon 1 plus Kp. Because the Kp formula is what we just saw, that is limit S tends to 0 G of S into H of S. Done? Good. So that is your step response. Your step response is a positional error constant. Step response of the steady state error for input step is 1 upon 1 plus Kp. In MCQs and in objective type questions, these are commonly asked, but not as a descriptive type question. Same way I can do this for my ramp and parabolic signals, where my R of S is going to be 1 by S square and 1 by S cube. And I can just make a guess right here that I'm going to get my output to be what? 1 by Kv and 1 by Ka, right? Because of that S square, I'm going to get that S into G of S into H of S, and that's going to be my Kv, velocity error constant, and then for my S cube, I'll be getting it as S square into G of S into H of S. That's going to be my acceleration constant Ka. Yes, so let's see how this simplifies to. So when I apply limit of, okay, so here I'm just gonna get it as 1 upon kv. I'm not gonna get that 1 plus, because my limit s to s becomes 0. So this is equal to just 1 upon kv. So I can write that as this is my 1 upon kv, right? Not next is, this is my ESS for my ramp signal. Similarly, for my parabolic signal, I'll be getting ESS is equal to 1 by Ka. You can just do it. You can just, it's a mind math. You can do it in your mind and you can get the answer as 1 upon Ka. It's all similar except that we're going to get S square GS HS, and that's going to come out to be 1 upon Ka. Good. So we have done some numerical. This can come, no, this can be considered as a numerical, because find the steady state error for a ramp signal. Find the steady state error when your input is a step signal, right? So that is, no, that can be considered as a numerical, what we just did. Now let's do some questions. So let's do a numerical now. So we're going to see if I would like to show you a few numericals on a steady state error for the given unity feedback. So whenever you see unity feedback, you all know that your H of S is equal to 1, and that is what is exactly, they imply by saying that it's a unity feedback system. So after seeing unity feedback, don't search the question for H of S. So where is my H of S? H of S is not given. What to do with the question? That should not come to your mind, because it's very clear that whenever you have a unity feedback, your H of S is equal to 1. Your G of S is given and your input is given to be 2 by S. So that is a step signal input. Now we need to find the static and steady state error. So when I'm, when the question says static error, they're asking us to find the Kp, Kv, and Ka. So those are the 3 static error constants we have seen. Then for your steady state error, you need to find ESS. Yeah, so we'll be using the limit S tends to 0, S into E of S for our steady state error. So let's quickly get to it. So let's apply Kp, Kv, and Ka formulas for this. So I know what is my G of S and I know what is my H of S, and my limit S tends to 0 is going to give me Kp as infinity, right? Kp will be now, because I have it 0 in the denominator, and that's gonna bring it to infinity. Okay, good. So that's your Kp, and what happens for my Kv? My Kv will take away the S in the denominator, so I'm definitely going to see some finite value, and that finite value is going to be equal to 2 into 0 plus 1, 2 upon minus 1. So my Kv should be minus 2. So my mind calculation or my mind math is telling it should be minus 2. Let's see what it comes to. It is coming to minus 2, yes. And what about Ka? So I'm going to have S square. So that's going to keep an S in the numerator, and that's going to come out to be 0. So my Ka is going to be 0. Again, my mind is telling Ka to be 0. And yes, so this is how you do these problems, right? So it's very straightforward, and you don't have to know much about even applying the limits and taking the fractional computation for your transfer function E of S. So it is quite simple, and your Ka comes out to be 0. Alright, so that is your static constant. So Kv, Kp, and Ka are computed and done. Now we will look for our steady state error ESS. So your steady state error ESS is equal to limit S tends to 0, S into E of S into H of S. Good. So your steady state error is given by limit S tends to 0, S into E of S. And I know what is my E of S formula. So what is the E of S formula? R of S divided by 1 plus G of S into H of S. So my R of S is given to be 2 by S. So I'll put all those fraction simplification and then apply the limit S tends to 0. And then let's see what do I get for my ESS. Good. That is my steady state error. So simplifying these fractions, you have to take the fractions to the simplest level before you apply the limit, because if you apply the limit before you do the simplification, you will definitely end up getting a wrong output. That is one of the rule set that I go with, or that is very much it is not you go with, it is very much needed and you have to follow it to the last step. So simplify to every possible simplification there is with the fractions, and after that you can apply the limits, and when you do that your answer comes out to be fine, right, or correct. So that is what I'm doing here. I'm doing the fractional simplification, and now I can apply my limits. So I'm having this, and now when I apply the limit, my limit is going to come out to be -1. I think the steady state error is going to come uh, that is what I'm writing. Before applying, you have to simplify. So the limit S tends to 0 will bring that to -2 upon 2 or -1. And that is your ESS or steady state error. Alright, so that is how you solve these questions. So we have done the static and the steady state error. So the complexity can be a little more difficult when you see some exam questions. But there also the steps are the same, but you run into fractions which are much which require more number of multiplications and factorization, expansions, and solving for the LCMs, least common multiple. All that will be in a much better more number of steps for a much complex question. So that's it. Then now ESS is okay. I forgot that S. So we have an S into 2S minus 2. So this is just E of S, and after E of S I have to take that S into E of S, and that makes it 0. So your ESS, the steady state error, is 0, which is good, because you may think why we are getting it as 0. 0 is good, means your error is 0, means it's a good, your system is a good system. So ideally we want always the error to be 0, and it is almost impossible to bring the error to 0. But in these numericals we are showing, we are getting as 0 error, which is a good thing. And the goal of the system design in control should be to minimize this error. So the control engineers must minimize the static error and also the steady state error to have an efficient system. Another question, same type, unity feedback, G of S is given, R of S is given. Find the static errors and find the steady state error. So I'm just gonna let you watch this, because the steps are pretty much the same. I'm gonna do the same. I'm gonna take KP, KV, and KA. I'm gonna put these and apply the limits. And then for my steady state error ESS, I'm gonna do limit S tends to 0, S into E of S. So for that, first I'll find E of S, simplify the fractional polynomials to the simplest form, then multiply it with S, then apply the limits, then I'm going to get my ESS. So I'll let you watch it through, because this is the last numerical for today's class. And I hope you followed. This is a very simple lecture today. What we do is we saw what is your steady state error and what is the final value theorem that lets us avoid the infinity computation or the infinity approach in the limits. So we're using the final value theorem. We do that, and then after that we saw what are the static error constants, and they are given by Kp, Kv, and Ka, followed by some numericals on how to obtain or how to calculate the static errors and steady state errors for your first order and second order system. I think the first numerical we saw was a first order system, and the second numerical we are seeing is a second order system, and this is what you get. You get a question in your exams or in your entrance tests for a first order system or a second order system. no more than that. It's either your first order or second order, and then we are just doing these steps. The same steps which we did for your first order system are applicable to this system also. So please watch it. I'll see you for next class with more interesting lectures. Thank you.